And Todd, that was an awesome presentation. I had no idea you were holding that out on us, and it had the visuals with the warp drive and all that. So, okay, so let me put you back up, and then let me see. Let me go to Eric first. Eric Hermanson, sir.
Hello, hello, Todd.
Hey, sorry.
Hello, Todd. Yes, how are you getting the neutrons? How are you getting the neutrons to get pulled?
They have a diamagnetic ratio too. It's almost identical to a proton, because it's not really the neutrons or the protons that are spinning. It's the quarks, and the quarks all have a charge and magnetic moment.
Okay. So, if the fields inside the craft are not, if the fields inside the craft are not perfectly uniform, you will rip things apart, right? You've got to have there can't be any mistakes at all in the structure, because then you'll rip your body apart.
Yeah.
But when this craft goes, will the person feel any acceleration?
They shouldn't. That's the objective, is that because it's causing all the particles that make up the ship and the passengers and everything in it, they would all accelerate together.
Mm-hmm. Now, would you call this the equivalent of if you can speed up the clock at the very front of the ship, I'm sorry, slow down the clock at the very front of the ship and speed it up at the back of the ship in a tremendous dilation and expansion of time, and you have the time, no time dilation inside the ship, then the ship would also move, correct?
Yeah, if you could do that.
Okay.
Yeah, the problem is projecting anything outside the ship. The way this works is that the field, the only thing you care about is where the field intersects those subatomic particles of the ship and the passengers and everything else. Anything outside of that is irrelevant. It's like it has to affect the particles, and then you're charging those particles up like you're ramping them up a hill and then letting them fall back down. And as they fall back down, they're going to radiate kind of like a laser, and you're basically, the gradient in the field is directing which way that's going to go.
But aren't the electrons in the cyclotron radiating due to Bremsstrahlung?
Yeah.
And so part of the energy loss you talked about, isn't that just plainly due to Bremsstrahlung?
Yep.
And you're adding that onto the equation. You're not incorporating that.
It's part of it. I mean, it's like I say, at the end of the day, when you're back at the bottom of the well, so to speak, when you're back to your starting potential, is that you have an equilibrium at the quantum scale between the losses and the 0 point field that supports it. So you've got this balance, this symmetry between the two, and you're charging up one side with a high potential and letting it fall back down, but that's as low as it can go. So, and this is all sublight. It's not FTL. Like I said, there's nothing yet to date that tells us how to make it go FTL, how to accelerate it beyond the speed of light. I hope it's possible, but from what I've seen so far in terms of just how much it's offset from the galaxy and the sun and the cosmos, it's like 1 part in a million. So if you could negate the effects of all those things in our local neighborhood, it would only raise the speed of light by 1 part in a million. So it's really hard to make it go faster.
Thank you. So Todd, let me go to Michael Boyd next, sir. There we go.
Hello. Hey, Todd.
Hey,
Um, I'm sorry I missed the beginning of your presentation. I was dealing with my taxes.
don't
and
worry.
But I'm curious about I heard you talking about the relationship between matter and resonance and that kind of stuff. I'm curious if you how that would affect the equations if you in a state where there isn't matter, like empty space. How would the gravitational field behave differently without the matter being there? I'm curious if you have considered that.
I mean, in empty space, I'm modeling. The model is modeling gravity as scalar magnetic flux density, as due to gradient in the scalar magnetic flux density.
So magnetic flux density.
Yeah, so it's like a magnetic flux density, but it has no direction. It's because it's random. It comes in any direction, any strength, any form, in a very wide bandwidth spectrum.
So if you were thinking about magnetism, positive, negative magnetism, it would be like an erase state.
Yeah, it'd be like you pretty much
like you erased it.
Yeah.
So all the little magnets were pointing whichever way. Correct.
Right. But the magnets are still there.
They're still there. They're just not. They're not polarized.
Exactly. They're unpolarized. That's the 0 point field. You erased it.
Okay. And then I heard you mention 0 point field, and I'm curious about your thoughts about, which I've asked this question of a number of other physicists, is do you think the 0 point field has a band gap like a semiconductor?
In a sense, it's got the electron-positron gap. If you put a strong enough electric field and hit the Schwinger limit, you'll create electron-positron pairs, which you could look at as dielectric breakdown.
So it does have a band gap. So basically, I think of empty space.
But you have to be in the presence of matter to do it. I mean, it's not gonna. It supposedly happens spontaneously, but there are some arguments against that. But in the presence of matter, it's much easier for it to happen, because electrons are so damn small and protons are so damn small that the field strength is enormous, and you can get to the Schwinger limit where particles and antiparticles can be created.
So the way I think about it is in a semiconductor, you have the N and the P side, and then typically you'll take a material and you'll dope it, or you'll hit it with something, and that'll make it a P side. Essentially, but the material has what's called intrinsic carrier concentration. And so what my thought is that the intrinsic carrier concentration of the protons in the flux, a proton flux, would create a magnetic flux like you're talking about. Because you have moving protons, that's going to create magnetic field, right?
So I think it's pretty much a product of the motion of everything everywhere.
Everywhere, exactly. Everything's moving everywhere. Yeah. And what I'm saying is in outer space, there's still protons moving, but the intrinsic level of those protons is different than what it is over here on Earth when we're sitting on this rock.
Yeah. And that's why, like in Hal's model, Hal Puthoff's model, which you referenced there, based on that model, the speed of light up in orbit, up by the moon is higher, it's faster than the speed of light down here.
Well, no, the speed is different, but the speed is the same, but the reference frame is different. So what Hal's saying is when you're in expanded space-time, where time moves faster, length stretches. Right. So the velocity stays the same. You follow?
No,
but from your frame of reference moving, it doesn't change. But if I'm looking at you moving really fast, it might look to me like you're moving faster than the speed of light when you're really not. It's just because from where I'm looking. And that's what he's trying to talk about when I couldn't really show that video of his, but he's talking about how, well, if one of these UAPs takes off really fast near you, you don't want to stand near it because you might get radiation sickness.
Oh, yeah. Yeah.
So it's thanks for your thoughts. I appreciate it.
Thanks, Michael. Okay, let me go to Will. Will, let me see. Thank you for joining us. I didn't know you were. Well, you've been here for a while, I guess. Just hiding out in the back. Oops, and Will just disappeared.
Yeah, just hiding out in the back.
Oh, there we go. Okay, no, you disappeared from my screen, the chat thing. Welcome back, sir.
Up until now, I didn't really have any good questions. So, or maybe any questions. So 2 questions really. So one, do you have a schematic where people can repeat your experiments? And 2, I noticed that you were talking about fermions early on in your presentation. How does the new discoveries at CERN, where there's now a belief of intermediary particles taking place in these types of reactions, where, so how does that affect your model?
Barely at all. I mean, in a sense, my model is that the universe is full of random magnetic flux, and what they found is there's extra magnetic flux. So that's what's throwing off the G-2 experiment. So there's extra magnetic flux there that they haven't accounted for yet.
Okay, but you still have your index of refraction and so on. So certainly there must be some effect.
Right. But they're not accounting for it. They're not accounting for gravity at all.
So do you think that's what the new thing is?
I don't know. I just came out. I haven't, 10 years from now, I might figure that out.
Yeah. So, and then also the first question, is there any way that people can replicate your experiment to determine, whether or not it actually works the way that you say? This is one of the weaknesses in this area.
Right. I publish pretty much everything onto ResearchGate eventually, and then Falcon Space has a database where they collect a lot of stuff, and we're totally open, open disclosure, open source lab. So, anybody that emails and wants it can have it. But eventually I will, when I get done with some real experiments, because this with the Lorentz force experiment demonstrator, that's like an off-the-shelf cabinet I bought, and then I wound a coil to cause a gradient, and it makes a nice demonstration of something that's too small to see, and it makes it macroscopic so you can see it. And that's a point I want to make sure everybody understands. It's not a warp drive. It's an illustration of what warp drive does. And, so you can see it visually, what's going on when you're spinning protons and neutrons and things. And then I have another experiment that I'm still working on with nuclear magnetic resonance and measuring the weight. And I had some setbacks with work and all, and not having a good enough power supply to run my Helmholtz coils. But now I have a nice new set of Helmholtz coils and a nice power supply to go with it. So hopefully I can get back to that relatively soon and have some data with that. And, that whole experiment write-up will be, on ResearchGate.
Yeah, well, I'm actually happy to hear about that. You're able to demonstrate how to make a gradient transformer, because I have gradient transformers that are using NMR in my lab, and they're quite expensive devices.
Yeah.
So, That's actually what I think one of the tricky parts is, making the gradients without having, anywhere from 15 to $80,000 worth of hardware.
Yeah, well, in this case, it's all low frequency, so I'm not dealing with megahertz. I'm dealing, with kilohertz and just a 2 centimeter diameter beam.
Okay, thank you very much.
Thanks, Will. Okay, so HT Alvarez had asked me to ask for him because he's having some sound and video issues. He's wondering if there's a direct quantifiable relationship between the warp bubble energy and the amount of gravity in the moving ship at any acceleration and speed. And that one's in chat, Todd, also. Okay. Yeah, sorry. So I think basically what this him or her is asking is what the energy relationship is, right? Like if you want to go X speed, then what is Y energy?
Essentially, if you're really doing warp drive, it should be Newtonian as opposed to relativistic, because there's no time dilation involved. And so if there's no time dilation involved, then energy doesn't go up exponentially as you approach the speed of light. And so your energy requirements become Newtonian, 1/2 mv squared. But in the case of sublight warp drive, like what I think I'm talking about here, it's relativistic. It's the same as any other form of propulsion. Momentum is conserved. You have to output, as much momentum behind you as you're moving it forward. And so you need a source of energy to move it. But at least the source is electromagnetic, not, gigatons of propellant.
Awesome. Well, thank you. Let me see. And then I think David Mathis had, where was it? I saw it here. Oh, David Mathis found the Bobrick and Martyr. He found the archive.
Yeah, that's the one. Martyr.
Okay. Yeah. And so I'm just trying to see if anybody else has questions here. Well, let me do this. Let me ask for anybody else to raise their hand if they've got questions for you. And okay.
I do have a few more videos on my YouTube channel, Warp Drive Tech. Like and subscribe. And if you have an idea of what I should try or comments on any of those videos, you can leave me a message there. I read them all. And I'm going to be doing more videos of all the experiments I'm working on.
Well, this was a great one. I thought this was a great presentation. It was kind of a different approach, right? Because you've presented on the NMR stuff in the past. This one switched things up a little bit. And then I liked the demo also. So I thought this was really cool. I'm really excited. Yeah. So thank you. Thank you for presenting.
All right.
Okay. Well, so yeah, let's do that. Oops. Okay, I will mute Todd out. And everyone, please, thank you for Todd.